Okay, please confirm if you can see the slides. All right, that's good. Okay, let's get started. The first topic is going to be on introduction to semiconductor materials. This is a bit of a recap of perhaps some contents that you've learned before. So just to crack the day, this is probably something that we don't have already now on the bus, on the train. So the part-time job as a semiconductor, right? So we used to have conductor on the train or bus. Now I think it's probably obsolete already, unless some countries still have it. But at least in our cases, it's already rare. So we don't have any more conductors available. Okay, and it's semiconductor. Okay. So let's just recap on what we have learned yesterday in the introduction. So can you just tell me again what makes the chips on the right? So if you see your phone on the left or your gadgets, laptops or iPad or something. So what makes the chips? What is in the chips? What is the semiconductor material inside? All right, yep, semiconductors. So what is in the semiconductor? Right, so silicon, right? So now we're using silicon to make the chips, okay? So this is only one of the examples that we have out of the many more that we have in the market. So we're going to learn a lot on silicon, and we're going to also learn a lot on other semiconductor materials as well. So the outline for today, we're going to look into primary types of materials. We're going to go through insulator, conductor, and semiconductor, and what differentiates insulator, semiconductor, and conductor in terms of their basic properties. And then we're going to go through a little bit on the review of crystal structure. This one you've learned before in 307, solid state physics. We're going to also cover crystallinity of semiconductor materials. So I'm not sure whether you have learned about crystallinity before. Have you? Have you learned anything on the crystallinity of the materials like amorphous and polycrystalline, monocrystalline? Have you learned anything like that before? All right, good. In which subject was it? Material science? Or some other solid state physics, okay? Yep, so we're going to recap on the crystallinity of the semiconductor materials in amorphous, in polycrystalline, or some even call it multicrystalline in certain conditions, and also monocrystalline or single crystal, and how this crystallinity of the materials affect the properties of the semiconductor and eventually the devices that we're going to learn later on in the second part of this course. So we're also looking into impurities and doping. So what is doping? So categories of impurities. You're gonna be taught on some impurities are desired. So you actually want those impurities in the lattice, and some other impurities are not desired or undesired impurities. You don't want them to be in the lattice because they're gonna affect the performance of the semiconductor materials or the devices badly. Okay, so we're going to look into P and N type doping as well. Have you learned anything on doping before? In any of the previous subjects? Okay, in which subject was it, Juwaria? Solid state as well, or material science, or solid state? Electronic as well, good. So some bits have been covered in electronics. All right, so in this case, we're going to look into more details of what's actually happening, not in this topic, but later on, we're going to see what is a p-n junction and how do we actually form p-n junction and what's going to happen when you join a p-type material and a n-type and an n-type semiconductor together as a junction. So what actually takes place before we can use the junction in our device. So there are basically three primary types of materials. So we can group them into three categories that are insulators, semiconductors, and conductors. So what differentiates these three different classes can be seen on this graph, can this on this chart. So you can see on the x-axis, on the top part of x-axis is the resistivity of the materials, and on the bottom part of the x-axis is the conductivity, which is the reciprocal of resistivity. So resistivity is given by this rho. Okay, you've learned about rho, RL over A and stuff like that. And then if you invert the rho, you will get conductivity. Okay, so you can see a range of conductivities and range of resistivities on the chart. So if you move from the left to the right, left to the right, so you will see increasing resistivity of material. Okay, sorry, reducing resistivity of material, from 10 to the 18 on the left to 10 to the minus 8 on the right. So reducing resistivity. And at the same time, you'll see the inverse, which is increasing conductivity from 10 minus 18 to 10 to the 8. So if you move from the left to the right, we are actually moving. Sorry, ada yang masih menunggu. Let me see again. Hold on. Yeah, I didn't see this. Oh, ada 8 orang lagi ya. Okay, thanks for the information. Amir, I missed that under the bar here. Okay, let me just put it on top so that I can click it easier. Okay, good. All right. Yeah. So going from the left to the right, so we are looking at reducing resistivity and increasing conductivity. So we are also going from insulator on the left, going through semiconductor in the middle, and going to conductor on the right. Okay, so that means if you want to relate to the resistivity and conductivity of the material, if you move from insulator to semiconductor to conductor, we are looking at reducing resistivity and increasing conductivity. Okay, so that means insulator has the lowest conductivity but the highest resistivity. So middle is middle because it's just the inverse. And conductor has the highest conductivity and the lowest resistivity at the same time. Okay, so examples of insulators are, so you can see here fused quartz, sulfur, diamond, nickel oxide, glass, okay, and many more. So can you give me some other examples of insulators in our real life? Apa lagi? What else? We have a lot, right? So can you give me a few examples in the box, or you might want to unmute yourself? Wood, yep, wood, kayu, wood. What else? They're quite obvious, right? Wood and what else? Wall, rubber, yeah, plastic, very good. Okay. So let's go to the right now. So plastic, yep, okay, thank you. So let's go to the right. So to the right, we have the highest conductivity and the lowest resistivity. So examples are typically metals, right? So like silver, copper, aluminum, platinum. What else? What are other metals that you know that are highly conductive? Any other examples? Yeah, gold, right? A lot more, right? Gold, palladium, carbon fibers, okay? Copper, okay. Right, so those are quite straightforward. When you talk about insulators and conductors, they're quite straightforward because they either conduct or don't conduct, right? So the conductors conduct electricity and insulators do not conduct electricity. So they are quite straightforward in nature. So in the middle, we have Semiconductors. So semiconductors are materials which have semiconducting properties in nature. So they can either, they will conduct, or um, the conductivity, if I can put it more accurately, the conductivity varies according to certain conditions. All right. So examples are like germanium, Ge, silicon. Silicon is the most common one that we're gonna in fact discuss a lot in this course. We also have binary semiconductors, which combines two elements in the periodic table, like gallium arsenide, which combines gallium and arsenic, gallium phosphide combining gallium and phosphorus, cadmium sulfide, cadmium and sulfur. Okay, what else? What other semiconductors do you know? Or in fact, since you're working on your FYP now, do you have any other semiconductors you would like to share that you're working on right now? I believe some of you are working on semiconductors, some are probably working on metals, and some are probably working on insulators. Anyone working on insulators at all for your FYP? Glass or something? Fuse, quartz? Anyone working on glass? Not you, okay. So what's your work, Haziq? Are you working on any sort of conductors or semiconductors or some other stuff? What's your material? How about others? What are your materials for your FYP? UC sensors. UC stands for? So you're working on sensors, and UC is what? UV. Okay, UV is straightforward, right? UV sensors, right? So what's your material? What's the material that you use for your UV sensor? What, zinc oxide or something? So while Haziq is typing, what are other semiconductor materials that you are working on? Some other students? Akila? How about you, Akila? Are you working on semiconductors or some other materials? Zinc oxide, see? Zinc oxide is quite common in our school. So I normally see zinc oxide. All right, zinc oxide. Okay, what else? Arisha, how about you? Arisha, Derwina Alani. How about your material? How about your material for your FYP? Or is it something else? That's fine. So you can relate eventually. Okay, I hope you can relate to the fundamental properties of the materials. Okay, just put it in the chat box. Okay. So yeah. So insulators such as fused quartz, glass have low conductivities. We've seen those conductivities and resistivities on the chart on the previous page. So in the order of 10 minus 18 to 10 to the 8. Okay. So conductors, on the other hand, have the opposite properties. So very high conductivity and very low resistivity. Okay. Unit for conductivity is Siemens per cm. Yeah, Siemens per cm, and resistivity is usually ohm cm. So semiconductors in the middle region have conductivities in between. So the keywords there are in between insulators and conductors. Okay, so it has a spectrum of conductivity and resistivity, and they depend on certain conditions. Okay, we're going to discuss that. I'm not sure the details, but I'm trying to work on a system to incorporate the UV sensor only, not to the okay, that's fine. It's okay. So yeah, so at least you know now you're working on UV sensor. So try to look into what sort of materials are you going to work on, because well, typically if you talk about UV sensors, your materials should have band gap in the order of above 2.5, 3 point something usually. If you talk about zinc oxide, it's somewhere 3.3 EV, electron volts, right? So that it falls in the UV region and does the job perfectly, right? In comparison to other low band gap materials. So semiconductors are sensitive to temperature, illumination, magnetic field, impurity atoms. We're going to discuss all this stuff later on as we go along the course, and we're going to see how these properties can be changed or can be manipulated, if you like, in order to make your semiconductor materials or semiconductor devices operate perfectly. Okay, this is for insulator. So insulator is very resistive in nature. So resistivity lies in the range of 10 to the 10, 10 to the 18 ohm cm. So you have seen examples just now, like glass, plastic, rubber, silicon dioxide, silicon nitride, silicon carbide, and yeah, we have a lot of other materials which fall into insulator category, right? So they don't conduct, right? They don't conduct electricity unless you can actually push them to conduct, but they don't conduct naturally. Okay? You have to do certain things extremely at high voltage or something in order to force them to do the job. So they don't because they have tightly bound electrons, usually 8, the valence electrons in the outermost shell. So when you have 8 tightly bound outer electrons, they don't move freely, so therefore they don't conduct. So in order for the semiconductor or the material to conduct, your carriers have to be able to move freely. So in this case, electrons and holes have to be able to wander around the material in the lattice in order to do the conduction. So if they are trapped, they are tightly bound to the lattice, they will not be able to do so. Therefore, there's no conduction in natural condition, right? So therefore, it's very difficult to get them to move even though with high voltage supply, right? So you can see at least in these illustrations down here. So if you talk about diamond, for example, as an insulator, so the band gap, is actually the gap between the upper side of your valence band in the middle. So at the bottom on the y-axis, okay, you nampak kat sini ya. So the distance between here to there, right? So distance between the top, the band edge of your valence band to the band edge of your conduction band, or the maximum point in the valence band to the minimum point in conduction band. So that's like 5.5 electron volt, and that's very big for a natural conduction to take place. So due to the large energy gap between the valence and the conduction bands, so if you look at the y-axis, this is the energy needed for us to push or to expel the electrons out of the valence shell, the outer shell, in order for them to be free and conduct. And that's just very, very big. Okay, that's why they don't conduct naturally. On the other hand, if you look at a conductor, so now you can see the difference here, down here in the illustration. So conductor is very conductive in nature. The resistivity lies in the range of 10 to the 4 to 10 to the minus 6, 10 to the minus 4 to 10 to the minus 6 ohm cm. So in comparison to the insulator, okay? So includes metals like what we've discussed just now. So this also includes heavily doped semiconductors, but this is a bit tricky though, because this third point actually belongs to semiconductor still, but the behavior is just like metal. Okay, so we call that a heavily doped semiconductor, or we call that a degenerate semiconductor. Don't worry yet, because we're going to come to this category later on in the course. It behaves like metal, but it's not metal, right? So due to the heavily doped nature. So if you put so much of dopant into the lattice, so at some point it will behave as if it's a metal, but it's not metal, it's a semiconductor. Okay. So materials in this case have loosely bound electrons, 1 or 2 in the outer shell, that can move freely under the influence of voltage or current, or actually in the natural state, they already have a conduction. So why good conduction? If you look at the energy band here on the right hand side, you can see we have overlap of region between valence band and conduction band. So that means the region in between, due to the overlap, so the outer electrons are already there to do the conduction, in comparison to this, where they have to actually cross the gap, right? Cross the gap in order to reach the bottom part or the edge of conduction band in order to do the conduction. While in this case, it's natural because of the overlap, right? So Now we come to the third category of material where the conductivity or the resistivity lies in the range of insulator and conductor. So resistivity in range of 10 to the minus 4 for heavily doped semiconductor to 10 to the 3 for undoped or intrinsic. Intrinsic here means undoped. So if you have silicon, for example, just pure silicon, you don't add anything into the lattice, we call that as intrinsic semiconductor or pure semiconductor. Right? On the other hand, we're going to learn later on, if you dope some dopants into the lattice of silicon, they are already considered dope, and in that case, we call the silicon to be extrinsic semiconductor or dope semiconductor. So intrinsic is pure, extrinsic is dope. Okay, so you can actually tailor the properties of your tailor the electrical conductivity of your semiconductor by including dopant into the lattice. Okay, so example of semiconductors, a lot you've seen just now on the chart. So for example, if we talk about elementary semiconductor, then we're talking about silicon and germanium. So it can be binary in nature, like gallium arsenide, cadmium sulfide, cadmium telluride. It can even go to ternary, like indium aluminum arsenide. You can even go to quaternary. For example, you can mix 4 different elements to form quaternary semiconductors as well. So it really depends on what do you want to have eventually. So it's normally driven by what type of devices or what the mechanism would you like to see in the semiconductor materials or the devices. Then only you come back and tune what sort of material and how much of that material do you need in the combination in order to result in certain properties that we're going to learn later on. So, for example, if you talk about, for example, what's the best example? Indium nitride, for example. So you can mix different fraction of indium in the indium nitride semiconductor in order to change the band gap of the semiconductor material in order for you to use for certain applications. So that's really application driven type of tuning. So you should know what do you want to use your semiconductor for. Then you come back to your semiconductor and tune the properties accordingly. For example, in this case, tuning the fraction of the indium in the indium nitride in order to result in certain properties that you can use for your application. Okay. So if you want to compare the energy gap for silicon in this case, so you have seen overlap of conduction and valence band for metals and such a huge energy gap for insulator, 5.5 for diamond, for example, 5.5 EV. And if you talk about silicon as a semiconductor, so the band gap in this case is about 1.12 EV. So it's not so small, but it's not that big as well, so it's in between. So that makes the properties of the semiconductor in between insulator and the conductor. These can in fact be tuned as well. So if you talk about germanium, the band gap is 0.7, 0.7 EV. If you talk about silicon, then it's 1.1. If you talk about gallium arsenide, it's 1.4. Cadmium telluride, 1.4. Indium phosphide, 1.5. So you have a range of different band gaps for different applications. Okay, so that's the beauty of working on semiconductors. You can actually work across the spectrum according to what you actually need. So this is the periodic table. If you look at silicon, so silicon is in which group? Where do you find silicon on the periodic table? Where's silicon? Group mana? Just to recap, senang, right? Yeah, group 14, right? Group 14 here. Okay, or group 4, we used to call it group 4 as well, group 14 or 4. Okay, so silicon, you have carbon, germanium, tin, lead. Okay, so silicon here is here. So in this course, we're going to talk about silicon a lot as the host atom. And then when we talk about doping later on, we're going to talk about dopant atoms relative to the host atom, which is silicon. So then we're going to discuss about which one has extra electrons, which one will provide extra holes in order to improve conductivity of the silicon. So you can also find, for example, what? Zinc oxide. You can also find cadmium, telluride. So you can work with 3,5 semiconductors. So if you look at 3,5, So if you look at this, okay, gallium arsenide. So gallium is with arsenide. What else? Indium with nitrogen, indium nitride. So you can have range of different combinations for your semiconductor materials. Okay, so portion of periodic table related to semiconductors. So on column 2, so you can go back to column 2 on your periodic table, and you can find magnesium, zinc, cadmium. If you go to group number 3, you can find boron, aluminum, gallium, indium. Silicon is in group 4 with germanium, tin, nitrogen, phosphorus. So you can come up with a different combination. Well, typically we have 3, 5, 3, 5, you combine 3 and 5, you combine 2, 6. Okay, for example, if you talk about First Solar that I mentioned yesterday, which manufactures cadmium telluride solar panels or solar cells. So they actually combine cadmium in group 2, cadmium here, and tellurium here in group 6. So hence the panel or the solar cell is called cadmium telluride, CDTE. Okay, so they combine cadmium and telluride. So they normally call it CadTel, cadmium telluride. So what else? Zinc, and hold on, somebody's coming. Okay, zinc and oxygen form zinc oxide, and what else? Gallium and arsenic forms gallium arsenide. Okay, indium, nitrogen, indium nitride. In fact, you can also combine silicon and germanium to form CG. Okay, so there are a range of different combinations that you can do in order to produce the properties that you want. So it's not limited. So semiconductor in definition, so we have compared so far the energy, electron energy on the y-axis for metal, which you have seen overlaps of conduction band and valence band, right? Conduction band on the right, on the top, and valence band on the bottom. So you can see the overlap. So semiconductor lies in between metal and insulator because they have not too small, not too big, a moderate band gap or energy gap. On the other hand, insulator has the biggest one. Okay. So if you move from the left to the right, so the conduction becomes harder and harder. If you move from the left to the right, the resistivity becomes higher and higher, and resistivity becomes higher and higher, and conductivity becomes lower and lower. Okay. So the band gap of silicon or other semiconductor is small enough, so it's quite moderate, not too small, not too big. Bias, thermal, optical excitation, or external factors can actually change or alter the properties of the semiconductor materials, which results in electrons having enough energy to move from valence band to conduction band to become available to carry current. So for electrical conduction to take place, the electrons, valence electrons, need to be free from the original binding. Okay, so that means they need to be able to be excited from the valence band to the conduction band in order to perform conduction. If they are not able to be in the conduction band, there will not be any conduction. So that's the ground rule. So whatever you do here, bias or thermal excitation, optical excitation, as long as the energy given to the valence electrons is enough to excite them from valence band to conduction band, then you will have conduction. If the external factors like bias, thermal, optical excitation given to the valence electrons is not enough, you will not get any conduction. So that is very simple. So if you understand that concept, then the rest will become straightforward. Okay. At room temperature, there are generally a sufficient number of electrons in the conduction band to support current flow, if you talk about semiconductor, but that depends on the doping level of the semiconductor. So later on, you're going to see if you incorporate dopants into the lattice, you can actually vary the level of the conduction of the silicon in this case. Okay. So silicon has about 1.12 electron volt, and insulator may go up to 10 electron volt. If you talk about diamond, it's 5.5 electron volt. So that's the difference that you can see in the energy required in order for us to excite the valence electrons into the conduction band to perform conduction. Okay. So we'll get to this when we talk about a band gap later on. So a little bit of recap. So silicon is in group 14 or group 4. It has 4 valence electrons in its outer shell. It's bounded covalently to another 4 neighboring atoms. Okay, 4 neighboring atoms. So this is what you have covered in solid state physics on the 3D periodic arrangement, or we call it lattice. So the smallest unit is a unit cell. So that's how it starts. We start everything from the unit cell. You've learned about BCC, FCC, and others, right? Hexagonal lattice. It depends on what type of semiconductors are you talking about. So if you talk about BCC, then common examples are like iron or chromium. If you talk about FCC, it's like aluminium, copper, gold. All right, so this is another recap as well. You have learned about crystallinity of semiconductor materials. So if you talk about crystallinity, so it is actually referring to the degree of structural order in solid. Okay, so how ordered is the solid in terms of the periodic arrangement? Okay, periodic arrangement. So the more ordered the material is, the higher the level of the crystallinity of the material. The less ordered of the material, so the crystallinity is becomes lower. Okay, so we're gonna see later on. In a crystal, the atoms or molecules are arranged in a regular periodic manner. So degree of crystallinity, so crystallinity of the material has a big influence on the hardness, density, transparency, diffusion, and other properties as well. So morphological properties, optical properties, electrical properties, in fact, thermal properties as well, all depend on the crystallinity of the material. So we have amorphous, we have polycrystalline or multicrystalline in some cases, and monocrystalline or single crystal. So we have 3 different groups if we talk about the crystallinity of the material. So amorphous material, for example, liquid and gap glasses, so represent a case where there is no order of the periodic arrangement. So we're going to see later on in the next slide. So if you don't have any order of arrangement, or you don't see any pattern of the periodic arrangement at all, then you can spot the arrangement as amorphous. So if you improve the crystallinity, on the other hand, you can see here, okay, if you look at the first one on the left, so there's no order at all, right? So there's no order at all of the periodic arrangement. So what about the middle one? What do you see? What do you see for the middle one? Polycrystalline. Do you see any order at all in the arrangement? Anyone? Yes. Okay, so now you see order. So how about the right one? Crystalline or single crystal or monocrystalline? Do you see order at all? Yes. Then what's the difference between poly and mono? Poly is in the middle and mono or single crystal is on the right. So what do you see the difference there? So both have order, then what's the difference? Apa bezanya? Direction of order, okay. 1 point, direction of order. What else? What is the obvious difference between the center and the right one? Arrangement, okay, Amirul. How about arrangement? Yep, Arena, arrangement, yes. So what do you see there? How about the arrangement there? Okay, let me see. One has multiple zone of crystal. Yes, so that's the answer. You have which one? The polycrystalline, right? So when you talk about polycrystalline has multiple crystals in the material. Okay, if you look at the center one, so you can see the very same order like monocrystalline, but it's limited in a region, right? So you can see this region is arranged this way, and the neighboring regions is arranged the other way. So each region belongs to different crystal orientation. Okay, yeah. So the other one just has a single one. Yeah, true. So you can see for polycrystalline, in this case, one is arranged that way and this way, and it's quite random, but then they are ordered. They have their own order in certain range, and they are encapsulated in a frame. And the border here is called grain boundaries, right? So one compartment there, if you like, is called grain, and that each grain represents one orientation, and the frame of that grain, okay, that encapsulate the grain is called grain boundary. So for polycrystalline here, you can see a lot of grain boundaries depending on the size of the grain. So if you talk about the small the very same area, if your grain size is very small, so that means you're going to have a lot of boundaries. So it's just like looking at the map of Peninsular Malaysia, for example. You have border for Kedah, Perlis, Perak, Penang, right? So Kedah in its own is a single crystal because it's one state to be represented with, and then the border of Kedah is the grain boundaries, if you like, right? And then Perak is another single crystal, and you have a border of Perak and Kedah and Penang, right? So you have a lot of grain boundaries there. So the smaller the country or the state is, then you're going to have more and more grain boundaries in the peninsula of Malaysia, for example. So on the other hand, if you talk about monocrystalline or single crystal or monocrystalline, normally when we talk about crystalline, we are normally referring to monocrystalline. But of course, if you put it as monocrystalline, it's going to be more specific. So monocrystalline, on the other hand, has only one arrangement of crystal. There's no other angle or something, right? So there's no grain boundary at all in the single crystal. So the boundary will be the edge of the material. If you talk about one 4-inch wafer, for example, so if you're working on a single crystal wafer, so that means the grain boundary will be the end of the wafer, the circumference of the wafer, because even though that's not the grain per se, so that's the edge of that crystal, because everything else on the surface is just one whole crystal, right? So let's look at the definition here. Amorphous, there's no recognizable long-range order to the positioning of the atom within the material. So there's no specific periodic arrangement at all. It's just messy everywhere, right? There's no specific arrangement. On the other hand, if you look at polycrystalline, you can see arrangement. Yes, you can see arrangement, but then you have multiple arrangements in the material. So in that case, we call it as polycrystalline. So in polycrystalline material, if you look at this, in every single grain, you have single crystal inside. So you have grain boundaries wrapping the grain. Inside, all single crystal. And the neighboring grains, all single crystal. But since you have multiple grains within the wafer, for example, then we call it polycrystalline or multicrystalline. So multicrystalline normally is the reference we use in solar industry if you talk about visible grains. You can see by using naked eyes, because some grains are really small that you have to go down to the microscope or SEM or some other stuff in order to see the arrangement to some extent. Some you may not be able to see at all. You might have to do XRD to see a couple of pics to see the presence of the grains or the different grains. And for monocrystalline, usually you can see by naked eyes by using by the color, usually, if you can. We can relate later on, okay? So, yeah, you have grain boundaries in between. So you have multiple crystals. So for example, if you want to relate to your crystal knowledge, right? Crystalline orientation knowledge, you may have 100 here and 101 here, 101 here, and some other crystal arrangement to be the neighboring arrangement, right? So monocrystalline, on the other hand, atoms are arranged in an orderly three-dimensional array infinitely, right? Infinitely. So it goes infinitely. So you cannot spot a single grain that is different from the central grain. Okay, so that's why we call it a single crystal, just one crystal within the material. So now let's look at this example, the real life example. So this is about solar industry, and this is about silicon solar industry. Okay, if you look at the first one, this is monocrystalline wafer. Okay, monocrystalline wafer. So on the right hand side is multicrystalline wafer, or polycrystalline if you like, in this case to compare. But the grains here are visible, right? You can see the grains, right? Can you? How do you see the grains there? Do you see anything different or any non-uniformity across the wafer on the right? Yep, right? You can see that because why do you see the grains? Why do you think you see the grains? Any idea? Many layers are not really many layers. Yeah, color tak sekata. Okay, kenapa color tak sekata? Why the color is not uniform? Why do you think so? To our eyes, we see something that is very crude. We see different colors. Yeah, done. Different colors. But why different colors? Various zone reflects light differently. Yes, perfect. Yeah, various crystals. So, for example, in this case, if you want to relate to the previous page, say 100, 101, and 101, whatnot. So each crystal orientation reflects the light differently at different levels. So to our eyes, we see different colors. Dark gray, light gray, slightly whitish and stuff like that. So it goes down or it boils down to the reflection level of every single grain that is not uniform. So so that's the physics inside. So what you see is very crude and very, very something obvious, but if you don't learn physics, you won't be able to explain. So now that's the beauty of learning this, right? If you go down to crystal orientation, so actually it's due to the different reflection level of light by different crystal orientation. So you may say that this one is crystal A, this one is crystal B, crystal C, and stuff like that. Okay, so this is multicrystalline. You can spot by your naked eyes because the grains are big enough to be spotted. The grains are visible. In some other cases, the grains are not visible, so you may not be able to see the grains like this because this is like cm in size. And if you to put this into perspective, if you talk about this wafer, it's like 6" by 6". Okay, 6 by 6". So if you talk about that grain size, that's perhaps a couple of centimeter in dimension. Okay, so that's centimeter squared kind of thing, rather than squared or micron squared. If you go for micron squared, you cannot see the grains to be visible. So for solar industry, for example, we normally refer to multicrystalline if the grains are big enough or visible. If they are not visible, we call them polycrystalline. But in other industries, we normally call this as polycrystalline generally. But if you talk about solar industry, we have a little bit um, other preference in order to name the grain by the grain size, in order to know that, oh, if you talk about polycrystalline, we know it already that they are not visible. If you talk about multicrystalline, we know it already that they are visible. On the other hand, if you look at this one, this is amorphous silicon. This is not on wafer because they are based on thin film technologies, where the thickness of the thin film, if you do the cross section of this thin film on plastic, because they are visible, they are flexible. Sorry, so the thickness of the thin film is usually in the range of 1 to 2 micron. It's like taking your hair, cabut satu rambut, your hair thickness is about 80 to 100 micron, say 100 micron, slice the hair into 100 pieces, and then you take one that's like 1 micron, and that's the thickness of amorphous silicon you use in this case, right? So amorphous silicon you cannot see, and it's amorphous in nature. There's no periodic arrangement at all, but you cannot see because it's still firm in nature, and you hardly see the arrangement on the amorphous. So what do you think? Let's just try to answer this question. Which one is the best? What do you think? The best is quite broad in nature. In this case, it depends on what do you want to say, and from which angle do you see that. So out of this, do you think which one is the best? Which one has the highest quality? For example, let's put it in a quality department. Mono, I think. Okay, all right. Single crystal. Yes. So the one with the highest quality is monocrystalline because the crystal is only one. So we're gonna see later on if you have mono and poly and amorphous, what's the impact to the properties of the semiconductor material. So in that case, you are saying mono has the highest quality, and on the opposite, which one has the lowest quality? Which one? The lowest quality between these three? What do you think? If you relate back to this, multi, poly, really? Rafai, what do you think? What do you think is multi? Okay, Juwaria said amorphous. Haziq, polycrystal. So Haziq and Rafai, you said multi and poly. Why do you think so? Any reason? You can unmute yourself, or you can write in the chat box. It's okay. Multi, Amiro, multi. So if you look at the crystalline arrangement, the lowest quality is, okay, let me read yours. Materials are usually financially like that. Not really. Okay, if you talk about too many crystal arrangement in one wafer, yes, but then that is subjective as well. That depends on the quality of the crystals grown by the process, by the specific process, because we have range of different processes to grow multicrystalline and polycrystalline. So if you look at this crystalline arrangement, the lowest quality is amorphous because they don't have any crystalline arrangement at all, and that will lead to a certain bad, what we call bad implication, or deleterious implication to the device or to the semiconductor materials in terms of the carrier lifetime inside. The carrier cannot survive so long, and the carrier will recombine so fast, it will just be diminished, gone from the system so fast, and they cannot conduct electricity anymore. Okay, we'll see later on, don't worry yet. So which one is the most expensive one, do you think? It's more on the processing side. Yeah, Go said mono. Yes, mono is the most expensive one because it's very hard to produce single crystal material in comparison to poly or multi or even mono. Amorphous. Amorphous is the easiest one to do. Okay. Okay, we'll see later on. Don't worry yet. That's just okay. If you look at this is actually my sample during my PhD. So this is a silicon thin film, 10 micron thick. So if you take one hair, you slice into 10. So you're gonna have a 10 micron thick. If you look at this angle, dari tepi ya. So the thickness of the silicon is, this is a bit angle, it's like 45 or 30 to 45 degrees. It's a bit oblique. So say I'm at one angle. But if you look at this, if this is the sample, if you look at this cross section, and the thickness is about 10 micron, 1/10 of our hair thickness. So this, the white part is the paint, I used in my solar cell. So this on the right hand side is silicon. So now you tell me, what is the crystallinity of the material? Is it amorphous or mono or multicrystalline or poly? Based on what we learned in the previous slides. So, what do you think? Mono or poly or amorphous? Ni yang kanan ni, the gray area. What do you think? Anyone? Poly, mono, poly, amorphous. So I see majority poly. Majority said poly, right? Poly. Anymore? One amorphous, one mono. So what do you see here? Isn't it the same with this? Isn't it the same with this? Right? You can see different reflection levels, right? Yeah. Right? So you can see a bit whitish in some areas, and then a little bit of light gray in some other areas, and some areas have dark gray in color. So it's poly in nature. So it's poly in nature. You can also call that multi in nature. So this one is multicrystalline or polycrystalline. So was my PhD last time. So what did I do? It was like 2016, 4 to 5 years ago, right? So what I did was I evaporated using electron beam system amorphous silicon like this, amorphous silicon on the glass substrate. The glass substrate is like 3.3 mm thickness, and I use laser, IR laser, infrared laser to scan. I just scan the laser like the scanner that you have 3-in-1 photocopy printer scanner. Just scan the laser on the amorphous silicon, so across the film, and you melt the silicon. So you melt the silicon. So upon solidification of the silicon, it will crystallize. So it'll form polycrystalline. So it'll follow the crystalline orientation will follow the seed layer there, and then it will follow accordingly, and it will form multicrystalline. So that's how that's one approach that we have in order to convert amorphous to polycrystalline. In this case, you can use laser. You can use some other different methods, and each method has its own advantage and disadvantage. So for this case, I use laser scan, infrared laser, wavelength of 808 nanometer, 808 nanometer, infrared laser, continuous wave. If you do anything, if you work anything on laser for your FYP, for example, perhaps you can relate more. So you just scan, and then after the scan, right after the scan, upon solidification, you turn the amorphous region into polycrystalline region, and then it will follow. So going from right to the left, so I scan from right to the left, so you can follow that. You can see that the grains are elongated in nature. Dia memanjang kan, dia memanjang ke kiri. You will follow. So because that's the mechanism of the scan. So it will form elongated grain, and within that single grain, you can see, for example, if you pick this white area or light gray area, for example, so inside this light gray is a single crystal, okay? But between this dark and white and whitish, you have grain boundaries. So you can see visible grain boundaries, right? So just like this, but it's elongated in nature, memanjang, so it's lengthened. So that's one of the examples I can show to you. Yeah, I think let's just stop here. We'll continue tomorrow, right? Tomorrow is 1 to 2 p.m. Tomorrow lunchtime, 1 to 2 p.m. We're going to continue on impurity and doping, okay? So is it okay so far? Is it okay? Can you guys follow? Good. All right. Do you have any questions so far? So far, so good. Yep. All right. Any questions so far that you don't understand, or anything you're not clear about the crystallinity and stuff? You can also have. I missed something to explain. Just 1 minute. You can also have microcrystalline. Microcrystalline is like combination of amorphous and crystalline in one sample. So that's not what we call a distinct category. So it's not like amorphous, poly, and mono. Those are the main 3 categories. But also, if you do research, you may also find your samples to have microcrystalline, in which, for example, if you have one sample, thin film grown on, I don't know, plastic or fabric or glass, you may have, if you do XRD or Raman, for example, you may find 50 or 60% of your sample is crystal, and the other 40% is amorphous. In that case, we call it microcrystalline. So they present together, crystalline and amorphous present together in one sample, in all locations across the sample. So in that case, you call it microcrystalline. But when you mention about microcrystalline, you have to mention about how much is the crystallinity of your sample. For example, it's given by XC, X, capital X, subscript C, XC equals to 60%, which means your sample has 60% of crystal and 40% of amorphous. Okay, there's one other category in between that I don't teach by default, but it's more on the research side. So at least you know that if you do research, you can also get two regions or 2 crystalline phases at the same time in one sample. Okay, so that's called microcrystalline. Okay, no question. I'll see you tomorrow then. Take care. Bye bye. Stay safe. Assalamualaikum.